Welcome back, everybody. This is AP Chemistry, and we're in Unit 8 and Section 2, doing some calculations with pH, pOH, and then finding the concentration of the hydrogen or hydronium ion, as well as the hydroxide. So there's going to be some equations that we need to know and be able to manipulate to figure those things out. The first thing that you're going to notice is that we have a Kw. Okay, this is going to be the dissociation constant or the ion product constant of water. So we see that we have water is a function of the hydrogen or hydronium ion as well as hydroxide ion. You multiply the two concentrations together and we're going to get 1 times 10 to the negative 14. So obviously what we're going to do with this is if you know this value, then we can focus on solving for the other value. Another way of finding these would be through the pH scale itself. And so the pH scale is a little bit different, but it's a derivation of this particular equation. So the pH scale does go from a scale from 0 to 14. And right in the middle, being neutral, is when we have 1 times 10 to the negative 7th of the hydrogen ions, as well as 1 times 10 to the negative 7th hydroxide ions. That is, by definition, a neutral solution. So if we see in the pH scale, we would see anything that's going to be stronger on this side. If my hydrogen ion is on this side, this is going to be acidic, and if we look on this side of the scale, this is going to be basic. There is actually a pOH scale, so we're looking at the pH scale right now. A pOH scale also goes from 0 to 14, but you'll notice that right in the middle is going to be neutral again. But if I have the pOH scale, this is going to be basic if it's less than 7, and acidic if it's going to be greater than 7, okay? Now, to relate this back into my hydrogen or my hydronium ion, okay, remember these are the same thing. H3O is the same thing as my H+. This is something that College Board uses quite often. This is going to be a scale that goes from 0 to 1. Okay, and so right in the middle of that is 1 times 10 to the negative 7. Now remember, if I expand that out, that means 1, 2, 3, 4, 5, and 6, and 7. So this is a small number, isn't it? So if I get even smaller in there, if I have my hydrogen or hydronium concentration is greater than this, that would be acidic. And if it was less than this, so it's like 1 times 10 to the negative 9, okay, that's going to be a basic solution. Okay, so that's if I've got my hydrogen or hydronium ion. But if I take a look at this scale and I'm describing my hydroxides, this is 1 times 10 to the negative 7, this is 1, and this is a 0. If I'm describing my hydroxide concentration, if I have more of those, then we would get basic over here, and this would be my acidic side. So we can manipulate these scales a little bit and just take a look at how they might apply to whatever situation we're going to be solving for, okay? That's my pH and pOH scale. Okay, now, if I take a look at some other ways of bouncing between those, if I'm given a concentration here, I can solve for my pH because the pH is the negative log of my hydronium ion. The pOH then is the negative log of the hydroxide. So just be careful when we're taking a look at, when we're asked a bunch of questions, make sure you're answering the appropriate question. Is this pOH that they're asking for or a pH? And these certainly are all interrelated, aren't they? If I know my pH, I can figure out my pOH by just adding them up and so on. So this is all we're going to be doing in this section, taking a look at those. And if we want to go the other way around and figure out these concentrations of hydrogen or my hydroxide, I would just take the anti-log. And the reason we would do that is because I'd be dividing by the negative log of something. Well, you can't divide by the negative log. Instead, we will multiply by the anti-log. Okay, so that's all we're going to be doing in this section. Let's take a look at a couple of these, and you're going to see some good trends. Okay, so first example with this, we see I have a concentration of 0.01 molar. Now, remember, this pH equals the negative log of my hydrogen concentration. Notice that this is an acid here, and we're being told this is a strong acid. That means it's going to dissociate 100% of the way. Okay, so then just plugging those values in now, 0.01, the negative log of this is going to end up with a pH of 2. Now I want you to notice something. If I were to write this in scientific notation, I would have 1 times 10 to the negative second. Since this is exactly 1, I can just look at this and say, oh, the pH is going to be 2. And so we'll see a couple of examples of this along the way. And that's just a shortcut. Without even picking up your calculator, you can find those concentrations. So if I take a look at this as being 1 times 10 to the negative third, since it's a strong acid, first of all, it's going to dissociate 100%. And also, I see that it's exactly 1 here. So since that's the case, and the reason that is the log of 1 is 0. So it's just the log of 10 to the negative third. Sorry, the negative of the log of 10 to the negative third. And so that will give me a pH of exactly 3. Okay, so straightforward with that. You won't even have to pick up your calculator if you see exactly 1. Now, remember what this means. If I see this, once again, if I was going to convert this into scientific notation, this would be 1 times 10 to the 0 power. It means it's the number 1 times 10 0 times. And so the pH of that would be a 0. Now, certainly you can still go in and go pH equals the negative log of 1. And so when I do that, I'm going to get a 0 value. Okay, so we can do some fast math with this without even picking up our calculator. Okay, now here's where we're going to be also saying the strong bases. Okay, so remember, and this is what I meant before by saying watch your units, because now if I'm doing this, I'm just going to be saying, okay, what is the pH of this? And I have a 1 times 10 to the negative second. Okay, so the negative log of that value is going to be 1 times 10 to the negative second. And so I just plug that in and I get a pH of 2. Now be careful, because that is the pH of it. And if am describing a base there, remember that the hydroxide ion is going to be in the value with it. So be careful, because I'm describing the OHs in this case. That doesn't match with pH. So what I solved for was actually the pOH in this, and that equals the 2. Okay, that's what I mean by watching those units. So if I plug that in, remember that pH plus my pOH equals 12. Okay, so my 2, so that means that this, or sorry, this equals 14. This would then equal 12. Okay, my pH is 12 because I was describing the entire time the hydroxide. Okay, that's what I want to do with that. There is another way that we could solve this, guys. If I say that this is my OH is 1 times 10 to the negative 12, well, remember that my hydrogen times my hydroxide is going to equal 1 times 10 to the negative 14, doesn't it? Well, if I plug in, this is going to be my X times 1 times 10 to the negative 2, that's going to equal 1 times 10 to the negative 14. Okay, so if I divide both sides by 1 times 10 to the negative 2, I'll get my X will equal 1 times 10 to the negative 12. Okay, that would describe my hydrogen concentration, or hydronium. So now I can find my pH from this, and since it's exactly 1, my pH would be 12. So you can do this either way. It doesn't matter which direction you go with it. Just watch out for those things. Most people end up going the just adding route of this. So if I'm describing my base as KOH, and my base is going to be 1 times 10 to the negative third, and so I take the negative log of that, I'm going to get a value of 3. But be careful, because this is hydroxide, I just solved, when I did the negative log, I just solved for the pOH. Okay, so 14 minus my 3, that'll give me a pH of 11. Okay, so pretty straightforward. Just practice that up again, and that's not too bad when we take a look at those types of examples. Now, what about when we see a case when we have something that's not going to be exactly 1? I see a pH of 2.2. I don't see a whole number here. Okay, so if it was exactly 2, I could just look at it and say, oh, okay, my hydrogen concentration is going to be a 1 times 10 to the negative 2. But let's take a look, and I want to just show you one of these things, because a pH is going to be on the 2.2. So my 2.2 equals the negative log of my hydronium ion. Once again, and I'll say it a bunch of times, that is hydrogen or hydronium, however you want to think about it. I want to get this just by itself. So that means I have to divide by the negative log, but you can't divide by log. So instead, we multiply by its reciprocal. The reciprocal, if you look on your calculator, there is going to be a button on there, and that's just your 10 to the x key. Okay, that's a second function right on the exact same as your log key for most calculators. And so all I have to do is multiply my 2.2. Now be careful, you got to take negative 2.2. You just hit your 10x key and negative 2.2. Some calculators you have to go negative 2.2 and then your 10x key either way. Okay, so just watch out for those types of circumstances. And when I do take the anti-log of that, I'll end up with a value of 6.2 times 10 to the negative third. And that's going to be a molarity. Okay? Now I want you to notice something with this. If I see the pH as 2.2, I want you to think, if this was 1 times 10 to the negative second, okay, then I would get exactly a pH of 2. But this is just a calculator check to make sure you're doing it right. Since this is not a whole number, the coefficient in front would bring the pH down a little bit. Okay, and so I see a 6.2. If I take the log of 6.2, that's going to take that value down a little bit. Then if I were to take the log of 3, okay, so I would have a pH of 3 if this is 1 times 10 to the negative third. I would have a pH of 3, and then the log of 6.2 would bring that down a little bit. That's how I got my 2.2. Short version of what I just said, if this coefficient is not exactly 1, I know that the pH of just 1 to the negative 3 is 3. And so I know that my answer is going to be right because it's going to be just slightly less than that pH of 3. Just a little calculator check, not anything you have to do with it. Just one of those good to know for security. Okay. Now I see I have a value of exactly a whole number. Okay. So if I see a pH of 9, then I'm okay. But be careful, this is my hydroxide, okay? But the pH of my hydroxide is going to be, since I'm given, we already know that my exponent is going to be 1 times 10 to the negative 9, and that's going to be describing my hydroxide. Because I'm taking a look at the pH is exactly 9, my pOH then would be, what would that be? I guess an 8. Oh, I would be describing my hydroxide. My pOH equals, let's see, the 8 in here. Or sorry, I misspoke. That's going to be a pOH of 5 because 9 plus 5 is 14. And so my hydroxide concentration then would be 1 times 10 to the negative 5. Okay, so notice we're okay with those descriptions because I'm already given the pH, and that corresponds directly with my hydronium. And if they were asking about my hydroxide, then I would have to go this other route. Okay, so that's all we need to do with those types of things. Just plug in the values, and you should be good to go. Now, let's take a look, and we have something that's going to be a weak acid. Okay, to this point we've been talking about strong acids and strong bases. Very simple calculations that we do in Gen Chem. But now we see that we have ourselves a weak acid. Okay, hypochlorous acid. We don't necessarily label these things as strong acids or bases right away, but take a look at my value. This is 3.5 times 10 to the negative 8. I already know how that it's going to be then a weak acid with it. So the question is, how much of this is going to dissociate? So I have to set up an equilibrium chart. I have to do my ice chart, don't I? I see that I have my hypochlorous acid is going to dissociate into my hydrogen or hydronium ion and my hypochlorite, okay? And so the question is, how much is it going to do that? Well, if I have my initial value of a 0.100 molar, and it's I put that into water, it's going to dissociate, and it's going to change a certain amount. We don't know how much, and notice that it's a 1-to-1 ratio for everything. Okay, so then all I have to do at equilibrium is I say it's a 0.1 minus x, and this is going to be x and x. Okay, so we solved this exactly like an equilibrium problem, and I saw that my 3.5 times 10 to the negative 8 is going to equal x squared over my 0.1 minus x. Notice this is in fact small, so I can ignore this, and disregarded, I should say. And so I just see that 3.5 times 10 to negative 8 equals x squared over 0.1. Multiply both sides by 0.1, and I'll end up, and take the square root, I'll end up with a value of 5.9 times 10 to the negative 5. Now, what did we just describe? We just described my hydrogen concentration. So from there, I would say that my pH equals the negative log of that 5.9 times 10 to the negative 5. Okay, so I find that my pH in this case would end up being 4.23. Okay, so remember I just solved for X, and that is my hydrogen concentration. That's all I need to do there. Okay, let's take a look at another one along the way, and we're going to be taking a look at another weak acid, and this one's going to be citric acid. I'm just going to abbreviate citric acid rather than write it out the whole time as HCA. Okay, so that's citric acid that I'm describing. So let's set up my equation, and I see that I have my acetic acid is going to go both ways and form my hydrogen concentration, and then the citric acid, this would be the conjugate base of my citric acid once it dissociates. So my initial concentration is a 0.2 in this case, and X and X, or sorry, and 0 and 0. And I'm going to lose, okay, for the change, it's going to be losing a value of X and gaining a value of X. And so my equilibrium becomes a 0.2 minus X. And so this is going to be X and X. And so my dissociation constant ends up being 7.45 times 10 to the negative 4. That's going to equal X squared over 0.2 minus X. Okay, but in this case, this is actually pretty big for that. So I can't necessarily disregard this particular value. Okay, the question is, how do we test that? Now remember, if I solve for this and I find, if I disregard it in the first place, I would find that my X is going to be 0.0122. Okay, if that's the case, then I would have a pH of, let's see, the negative log of the 0.0122, and so my pH would end up being 1.91. Okay, but I want you to notice something. I have the 0.0122. Let's put it to the test to see, is this something I can disregard? So if I do that, 0.0122, remember how to do these with equilibrium problems? I put that over the original concentration, and I end up with, and multiply that by 100%, and I see that it actually comes me to a value of 6.1%. Uh-oh, that doesn't pass the 5% rule, does it? So now I have to go back and I have to actually account for that X. So let's go ahead and do that. My 7.45 times 10 to the negative 4th, okay? That will equal X squared over 0.2 minus X. Okay, now we cannot disregard this. So I'm going to multiply both sides by my 0.2 minus X. Multiply both sides by that, and so I'll end up, excuse me, I'll end up with, combining like terms, I'll have X squared plus 0.00075, and that will, let's see, that's going to be X minus a 0.00149. That will equal 0, okay? So here's my A, here's my B value, here's my C value. Let's go ahead and put it into the quadratic formula. X is going to be negative B plus or minus the square root of B squared minus 4AC. And that's going to be all over 2A. Okay, so let's go ahead and plug in those values. There's my A, that's going to be a 1, and that's a 1 there. Here's my 0.0149, that's my C, I put that there. And my 0.00075, that will represent my B values. If I do this, the math will end up being X will be, let's see, a 0.0118, or it'll end up with, accounting for the negative value in here, that'll be a negative 1.18 times 10 to the negative 2. Okay, obviously you can't have a negative in there, so that's not an option. So my pH is going to end up being the negative log of 0.0118. Okay, if I do that, I'll end up with a pH of 1.93. We had to do that. Now notice the difference. It's not a whole lot, but it is a significant amount. 6% is significant enough. This is my actual answer, accounting for that X. Okay, so just be careful with paying attention to what we know with regards to our equilibrium problems. Okay, now let's take a look at this. When we see pH of a solution that contains equal amounts of both my cyanic acid as well as my nitrous acid. Okay, so we have two things to account for here. Okay, if I'm going to be doing that, we've got to keep track of everything. So my major species in this case, my major species is going to be obviously going to be my acids. The HNO2 as well, and there is going to be water. Now, water doesn't really do anything, it just kind of activates those things along the way. But remember that when I have my water accounted for in here, my HOH is my water, and that's going to dissociate into my hydrogen ion as well as my hydroxide ion. Okay, and so if I do that, my hydrogen concentration would then be 1 times 10 to the negative 7. Okay, so that's because it's water, it's neutral in that case. Now with my cyanic acid, okay, this is cyanide, and so then I would just throw the hydrogen in front, cyanic acid. If I do that, that would dissociate into my hydrogen ion as well as my cyanide ion. Okay, my hydrogen ion, they tell me in this case, I would end up seeing with this if I look this up, I would see that my hydrogen concentration, again, I just looked this one up, is a value of 2.49 times 10 to the negative 5. Okay, now if I do all of this work, then I would see, okay, if I put this into an equilibrium, that my initial of my cyanic, remember my initial was going to be the 1 molar, so that's going to end up being a 1 minus X. That will equal, if I'm taking a look at my hydrogen as my X, and then my anion that's going to be there would be my Y value. So 1 minus X, that will then dissociate into my X and my Y. Okay, so again, I'm just kind of bypassing the entire ice chart with this because we know how that works. So I would end up with my Ka for this would be 6.2 times 10 to the negative 10, okay, because that's given here. And that's going to be a function of my X and Y, okay, so that's going to equal my X times my X, if you kind of go that route, over my 1.00 minus X. Again, we want to know what those values are. If I do this, I'm going to be multiplying both sides by 1, okay, and this is going to be a small number, so I can disregard this. So it's just 1 in there, and so if I take a look at that, I would end up with 6.2 times 10 to the negative 10 equals X squared. Okay, if now taking a look at that, I can plug the value in now for my nitrous acid. Okay, nitrous acid ended up being a 5.00 minus X, and then I'd have my hydrogen ion and my nitrate ion. Okay, that would be an X, and that would be an X. Okay, so if I do this, I would end up with a Ka value here of 4 times 10 to the negative 4 would equal X squared over 5 minus X. Okay, so if I solve for that one, then I would just take a look and multiply both sides by 5. Again, I've got a small value here. It will end up being small. And so my hydrogen ion in this case ends up being 4.5 times 10 to the negative 2. pH, then, if I am just kind of taking these values and putting them in, my pH value would then be the negative log of 4.5 times 10 to the negative 2. And so my pH ends up being 1.35 along the way. Okay, so all I was doing is taking a look at one value and then plug it into the next value. Okay, that's all I need to do with that, and basically just account for all the species with it. Okay, so next problem as we take a look at these. Okay, if they had equal amounts, we could do it that way. Now we're going to find and figure out that percent dissociation then. Okay, so we've done this before to put it to the test to see if it's going to be passing the 5% rule. So this shouldn't be too terribly difficult for us. Notice that we've got, in this case, we have 1 molar solution of acetic acid. This is a weak acid in there. And so the question is, how much is it actually going to be dissociating? So I kind of take a look at it this way, and I see that I've got my acetic acid that will dissociate into my hydrogen ion and my acetate ion. So C2H3O2 with a -1 charge. Okay, so if I plug in my values, this is a 1.00 minus X, this is X and X at the end. Again, this is after equilibrium, and so I end up seeing that using my value, 1.8 times 10 to the -5 will equal my X squared over 1.00 minus X. Okay, we can disregard it because it's a small number, and so I just take the square root of that. I'll end up with an X equals 4.2 times 10 to the -3. Okay, now to figure out my percent dissociation, it's again just putting it to the test to see if it's a 5% rule. And so I put that over the original concentration of 1, and so I'll end up and multiply by 100%, and so I'll end up with a 0.42% dissociation. Okay, so it's not going to dissociate very much at all with that if it's at a 1 molar solution. Okay, next problem, taking a look, and let's see what the effect is by taking 1/10 of that concentration. Okay, once again, this is going to dissociate into my hydrogen ion and my acetate ion. So C2H3O2 -1. And so again, this is a 0.1 minus X, X and X. And so I have 1.8 times 10 to the -5 equals X squared over 0.1 this time. And so if I solve for that, I'll end up with a value of 1.3 times 10 to the -3rd. Okay, just finding and taking the square root of that. So I divide that by my original concentration of 0.1, and so I'll end up multiply that by 100%, and I'll end up with a dissociation of 1.3%. Okay, so if I just take a look at those strengths and see how much it's going to dissociate, what percent of it would dissociate. Okay, pretty straightforward with those. Just keep track of your math along the way. Now let's take a look at this in terms of, let's see, the uric acid. I have a 0.5 molar solution of that, and we see that it is 1.6% dissociated, and this time we're solving for my dissociation constant. Okay, so it's again just doing the exact same stuff that we've done along the way. So let's take my uric acid, so C5H3N4O4. That's going to dissociate into my hydrogen ion and my uric acid, basically my uric acid conjugate base. I'll just abbreviate it that way. There's my X, and this is going to be a 0.5, losing a certain amount of X. Okay, so I don't know what my, we want to know that dissociation constant. We have to calculate for it. So I'll look up my value, or I'm basically going to be applying for this along the way. Now I know that it's a 1.6% dissociated. So what that means is 1.6% is dissociating of this conjugate base here. So that's going to be my concentration of my C5H3N4O4 to the -1 over my 0.5. Okay, and I'm going to multiply that by 100. Okay, so if I do these types of things, next step is then going to see, remember that this times my, that's going to equal also the same value as my hydrogen ion, isn't it? And so that's going to end up, when I multiply this out, this ends up being a 0.0080 molar solution. Okay, now if I plug in those values, okay, remember these two equal each other, so that would ended up being a 0.008 when I apply this math, 0.5 times a 1.6, and so I'll end up now plugging it back in, and remember that my Ka is going to be my X times my X over the 0.5 minus X, and so 0.008 times a 0.008. Remember, these are each to the first power because there's a coefficient of 1 in here, and that's going to be 0.5. Now, again, we don't know the Ka value, so I don't know if it's going to be large or small, but I do know my X value, so let's go ahead and subtract off the 0.008, and I find that my Ka value ends up being a 1.3 times 10 to the -4 then. Okay, so it's just going through and applying the math. I have to get this percent out of here. That's why I multiplied by 100. And so basically just kind of follow those to find the values for x, and then we plug it into our equation for solving for that constant. Okay, a couple more for you. This ends up being a long one. Let's take a look at doing this again. We're going to use lactic acid this time and see what it is in terms of percents this way. Okay, so again, we're going to follow the math with this. Here's my acetic or my lactic acid, C3H5O3. That's going to dissociate into my hydrogen and my lactic acid conjugate base, which is C3H5O3 with a -1 charge. Okay, and so my original concentration, we don't really know with that one, that's just because we should have that's a point. We could say a 1, we could say a 0.1. Let's go with a 0.1 concentration, and so I'm going to be subtracting off a certain amount. Here's my x, and so then I would say that the second step then is to say I've got 3.7% is going to equal this concentration of my conjugate base. So that's a C3H5O3 to the -1 power. That's going to be over my 0.1. Okay, and so multiply that by 100, and that will give me a value then of 0.0037. Now, remember that my hydrogen is the same as this because they're both x's in there. So then if I'm going to find my Ka value, I would just say that that's my hydrogen concentration, which is a 0.0037 to the first power, times my lactic acid conjugate base. So it's a 0.0037, again to the first power. And that's going to be all over my concentration of my lactic acid. That was a 0.1 minus my 0.0037. Okay, and so if I do that math, I'll end up with a Ka value of 1.4 times 10 to the -4. Okay, that's all we need to do with those types of problems. Okay, let's now flip over into just a couple of problems, flipping over into my hydroxides. Okay, calculate the pH of bases when I have this, and we do have another chart that we're going to be seeing with those values. Let's calculate the pH of a solution of hydroxides. Now, we've done a couple of these problems already. Let's just kind of revisit some of those along the way. This is a strong base, so it's going to be dissociating 100% there. So that is a strong base. So this is pretty simple because my sodium hydroxide will break down into my sodium ion as well as my hydroxide ion. Okay, and it'll break down fully. So there are a couple ways we can do this. Okay, so way one, we would take my hydrogen concentration times my hydroxide concentration, and that will equal 1 times 10 to the -14th. So this is way number one. Okay, you get to pick whichever one you want. My H3O concentration is going to be multiplied by 0.05, and that will total a 1 times 10 to the -14. So my hydrogen concentration would end up being 2 times 10 to the -3rd molar. Okay, now we would then just say pH is going to be a negative log of the 2 times 10 to the -3rd. And so my pH would end up being 12.70. What did I do? I took this value of hydroxide and I plugged that right in here, and then I solved for my hydronium, and then I turned that into pH. That's way one. Way two, which most people end up going this route just because it seems a little bit simpler. If I see my pOH equals the negative log of my hydroxide concentration. Well, I know my hydroxide concentration, and so my pOH ends up being 1.3. Okay, now I'm not done because they were asking for pH. So 14 minus a 1.3 will give me my pH of 12.70. Okay, so it's the same either direction with that. Now that's for a strong base. Let's take a look now at a weak base. Okay, we're going to just follow the same pathways we've done before. Just keep track of what we're doing. I see a pH, and this would actually end up being a weak base. So my ammonium plus my water, so HOH, would dissociate into ammonium ion. Ammonia becomes ammonium, and we get the hydroxide. Okay, so we would see in this case that, in fact, this serves as a base because it accepts the hydrogen from the water. Okay, so I see it's a very strong solution with 15 molar. I'm going to be losing a certain amount of that, and these are going to be gaining that amount. Okay, so if I see my KB value, my KB value ends up being a 1.8 times 10 to the negative 5. That will equal x squared over 15 minus x. Okay, my x ends up being a 0.016 molar. Okay, now watch out because that was my KB value. So what did I just find? I will be able to take this x, that would be describing my hydroxide concentration. Okay, so my pOH is going to be the negative log of 0.016, and so my pOH ends up being, in this case, lost my spot. My pOH ends up being a 1.80, so that makes my pH is going to be a 12.20. Okay, I just subtracted that from 14. All right, so all I'm doing is keeping track of what's being described here. Let's do one last one, and that'll wrap up this particular section. Okay, and then we're taking a look at a solution of methylamine. Okay, the methylamine, it is going to be a 1 molar solution in here, and I want to know the pH of that. Okay, so notice with this, it's a CH3 NH3. What's going to happen with this is it's going to react with the water. It's going to dissociate, and it's going to be forming CH3NH4. So basically what it is ammonia with the methyl group on top of it. Okay, and then I would end up with my hydroxide being produced. Okay, it is a 1 molar solution. It's going to lose, and this guy's going to gain, this guy's going to gain. And so I would then take a look at these values. My looking this one up, I would see that my KB value would end up being 4.38 times 10 to the negative 4. That's going to equal x squared over 1 minus x. Okay, and so again, I just looked that value up, and I would see my x equals a 0.021. Okay, that is my x value describing my hydroxide. So my pOH is going to be the negative log of 0.021. Okay, and that would give me a pOH of 1.68. Again, subtract that from 14, my pH ends up being a 12.32. Okay, so pretty straightforward. You just plug these values in. They're not too bad once we take a look at just tracking things along the way. Okay, bases are calculated the same way as acids. We should be able to do all of these problems.